talking about very specific graphical models, in particular, I'll be talking about spin system. And what's a spin system? The spin system or a graphical model is just a collection of random variables with the following property, following very abstract-looking property that you sort of put the random variables on a graph. Each random variable sits on a node in a graph. And then the distribution of these random variables has this property that if you take three sets S, U, and T of these random variables, such that in the graph, S is disconnected from T by U. So if I remove the nodes in U, then S and T become disconnected. Then the random variables in S are independent of the random variables in T, conditioned on the random variables in U. So such a distribution is called a graphical model or a spin system. And it looks like a very abstract property, but if one thinks about it, it's like a spatial version of the Markov property. And so the useful enough property that it shows up in many applications in physics. That's where the name spin system comes from. In fact, that's the first place where these things were studied, but also in modeling social networks and other inference problems. And the kind of questions that often one is interested in with these models is that if such a distribution is implicitly defined, then you want to approximately sample from it. You want to sample configurations from such distributions. And the other thing which is related is to compute marginals of the distribution. You have the distribution, and you might want to compute what is the probability that a given vertex, given random variable, has a certain value. And something that is still related, but somewhat different, but still turns out to be equivalent algorithmically in many settings, is approximating something called the partition function that I'll come to soon. So let's look at very specific examples, simple examples of these objects. So probably the simplest is something called independent sets in computer science and the hardcore lattice chaos in physics. So what you have here is a graph. So that's the graph. The random variables are going to be just assignments of plus or minus to the vertices. And the distribution is supported only on those assignments in which no two adjacent vertices are plus. So two adjacent vertices cannot be both occupied or plus. Okay. And then we put the distribution in such a way that the probability of seeing a particular such configuration, a particular set I of occupied vertices, is proportional to some number lambda raised to the size of this set. Okay. So the partition function then is just defined as a normalization constant in that distribution. The distribution is proportional to this weight, and the probability is therefore equal to this weight divided by this sum of all the weights over all the possible configurations, and this sum over all the possible configurations is called the partition function. Okay. And so one question that one could ask about this model, just from its commutative structure, is to just count the number of possible configurations. How many allowed configurations are there? This is just given by the graph. It does not depend upon lambda. That's the question of approximating the number of independent sets in a graph. And a general version of that would be that you're also given a lambda, and you're given the graph as an input, and you want to approximate this partition. No, this is just independent sets, all independent sets. So in particular, the empty set is also there. And if lambda is large, then the maximum independent set has the highest weight. Right? If lambda is bigger than 1, then the maximum independent set has the highest weight. If lambda is less than 1, that's not the case. So we'll see that this matters. How large lambda is matters for how hard or easy these problems are. Yeah, so the independent set in a graph is just such a coloring where no two adjacent vertices are both allowed to be black, but they can be white. Yeah, so this is just generating, yes, if you're from commutatorics kind of a terminology, that it's just a generating polynomial of all such configurations. So you're going over all such two colorings or all independent sets in the graph. For each independent set, you have a weight, which is lambda raised to the size of the independent set. And this weights generate a probability distribution, which is just this weight divided by this normalization constant, which is called the partition function. This graph is not an independent set, but these black nodes are form an independent set. I mean, the graph is not an independent set. Yeah. So, I mean, it's the independent set in this graph. So these things go over independent sets in the given graph. Okay. And so the approximation problem here is to approximate the partition function. And I won't go into details, but one can show that this problem is equivalent to sampling from the corresponding distribution. So if you can approximate this, then you can approximately sample from the corresponding distribution called the Gibbs distribution. The distribution over independent sets is just So mu of I is just 1 over z t of lambda times lambda. So it's proportional to these weights, and you have to normalize appropriately. So this computing the normalization constant is often equivalent to sampling. So, but I'll just concentrate on this computing this normalization constant. Okay, so this is one example. Another example is the Ising model. So yes, this in fact is the oldest. That was the simplest, and this is the oldest. It goes back to 1925. And here, so I'll use a slightly different kind of notation. So what we have is again a graph. Again, the possible configurations are again plus or minus assignments to the vertices, but the weights are not different. Every configuration is now allowed. All the 2 to the power n configurations are allowed, and for each configuration you have a weight that looks like this. So you have a lambda parameter, and you get a lambda raised to the power of the number of plus spins, so the number of vertices that are assigned plus, and then you have a beta parameter, and you get beta raised to the number of cut edges. So these are edges that are red in here. So the edges where there's a disagreement. Okay. So for those of you who might have seen this before, beta corresponds somehow to the inverse temperature, if you know what that is, and lambda to the field, but let's not worry about that. The model is completely defined by just these 2 parameters. So there's one parameter lambda, one parameter beta. The weight of each configuration, which is just an assignment of plus or minus spins, is given by this. And now the partition function is the sum of these weights over all these labeled cuts. And again, the question would be to approximate the partition function on a given graph with fixed beta and lambda. So one thing about the Ising model that will come up later in the talk is that the value, so there's a big qualitative difference that happens at in the value of beta. So so this is log beta on the, if you have beta bigger than 1, then you favor disagreement, and if beta is less than 1, then you favor agreement. So these two regimes of the model behave very differently in a qualitative sense, and we'll see some of these differences. So this side where you favor agreement is called ferromagnetic. The name comes from physics. So this is how ferromagnets, so like things like a material like iron is supposed to behave. And this is not so physical. This is called anti-ferromagnetic. Here you favor disagreement. So this is not motivated from magnetism, but comes from the same. So we'll see some of the differences between these 2 things later. So more generally, one could have bigger such models. You could have a graph or even a hypergraph. So hypergraph is just, so in a graph, each edge is just encompasses 2 vertices. You can encompass more vertices, and that would be a hypergraph. With some number of vertices and hyper edges. The configuration would, so we'll always be looking at configurations which are plus or minus, so binary configurations. We can have arbitrary edge potentials. So for each edge, we can say what weight we'll put if the vertices in the edge have a certain configuration. And then we can also have vertex potentials. So these edge potentials correspond to beta in the previous example. These vertex potentials correspond to lambda. And then one can define the partition function just as before. So you go over all the configurations, you multiply all the vertex potentials, all the edge potentials, and that's the partition function. And one could ask for approximating or sampling from such distributions. So the Ising model, yes. So I should say, so where it comes from. So the original motivation was magnetism, but recently it has also become a reasonably popular model for opinion formation or opinion dynamics in social networks. So it turns out that a very well studied kind of dynamics in the economics literature called the logit response dynamics, it corresponds exactly to something called the heat bath dynamics, which has this model as the stationary state. So let's not worry about it. So this model, it's abstract, but it comes up in several modeling situations. Okay. So our goal is going to be, so as I said, the sampling and approximation partition function are equivalent. So I'll just define what kind of approximation you want for so that you might be able to do sampling. So this notion of approximation that we'll be looking for is this fully polynomial time approximation scheme. So the input here would be the graph and the approximation parameter epsilon. You want to output an estimate of the partition function. In runtime, that is polynomial in the size of the graph and 1 over epsilon. And you want the guarantee that the difference should be relatively small. So relative to the actual value of the partition function, the difference should be small. So you're always measuring the difference relative to the actual value, and that should be smaller than epsilon, the parameter that you have. There's also a randomized version of this. So this is for deterministic algorithms. You might have a randomized algorithm. The algorithm runs with its own randomness, and then it produces some estimate. Now there will be another parameter delta, which is the probability with which the algorithm is allowed to err. And now you'd want runtime that is polynomial in the size of the graph, 1 over epsilon just as before, but logarithmic in 1 over the error parameter. And you want to have the guarantee that the errors are small in the same relative sense as before, with probability at least 1 minus delta. But so most of the time we'll be looking at the deterministic. So just to recap the terminology that we have seen and things that I've claimed without proof so far. So there are partition functions and Gibbs measures. So partition functions are basically the normalization constant in Gibbs measures. This is for independent set. The distribution, like here, is proportional to the weight, and you have to normalize by the partition function. And the thing that I've been claiming is that approximating Z, which is the problem we are going to be looking at, is equivalent algorithmically to approximately sampling from the distribution. If you can do one efficiently, you should be able to do the other efficiently in many cases, including the two cases that I showed, the Ising model and independent. So then the question is, what are the methods that one can use to do this approximation? So the two classical sort of methods, or maybe the only one classical method is Markov chain Monte Carlo. MNC should be capital, but so you sort of run some kind of a Markov chain which has this distribution as a stationary distribution, and you show somehow that this Markov chain will converge quickly to the stationary distribution, and then you use this equivalence in reverse to compute the partition function. So that's one way of doing it. So this is something I won't explore, but this is the thing that has been most widely studied. The second thing, which is maybe more recent, is exploiting something called correlation decay phenomenon. So we'll look at much more detail later on. So you exploit some structure of this distribution that it has to directly try to compute this. We know in the sense that we know this implicitly, but more than that, we don't. So what do you mean by? No. So here the input is the graph. So the input is always the graph. The distribution is defined. So this is more an estimation problem rather than a learning problem. Yeah. So I think I said that. So, yeah. So you want to estimate things rather than learn them. So I mean, you can ask interesting learning questions in this setting as well, but that's not what I'm. Yeah, but this is a very implicit description. You cannot do anything with it as it is. I mean, it will take exponential time to do any kind of estimation with this description. So the question is, how do you efficiently compute either marginals, compute the partition function, produce samples? Okay. So this is yeah. So this is so these are the two main techniques that have been used, and they both. So the name correlation decay appears only here, but they both build upon a particular notion of phase transition in physics based upon this phenomenon of correlation decay. And so let's look slightly more carefully at what these algorithms look like or what they do. So let me first just mention a result. So one example where you can use this correlation decay method to approximate the partition function is the anti-ferromagnetic Ising model that I mentioned earlier. So this is the case where you favor disagreement. So you have remember that you have two parameters, beta and log lambda. I mean beta and lambda, but here I'm plotting log lambda. And what you can do is you can draw a curve in this space, and I'll say what curve is later on. I'll just call one side of this curve correlation decay region. The other side has a no decay of correlations region. And one can show that in everywhere here in the non-red region, there is an F beta. Okay. So in this correlation decay region, which I'll say how it comes, where it comes from, there is a F beta, and this is in fact tight. In this red region, so there is this line separating the two regions, just a thin line. I mean, there's no thickness to it. On one side of the line, there is a deterministic F beta. On the other side, there is no efficient algorithm unless a lot of other problems become easy. So basically, NP is equal to RP. So unless you have randomized polynomial time algorithms for solving things like traveling salesmen and so on, you don't have fast algorithms for approximate the partition function here. So this phase transition, so you see a complexity phase transition here, and what we'll see later is that the complexity phase transitions comes from a so-called correlation decay phase transition that has been well studied. Okay. So this is, so okay, so this is the NP hardness result. So this is algorithm agnostic. What you can show is Markov chain Monte Carlo, you can unconditionally show that it won't work in this region. But what we don't know is whether Markov chain Monte Carlo works all the way up to the line. So this we don't know. But we know that this correlation decay method, which I won't describe what it is, can be used to go all the way up to the line. It's different from Markov chain. Okay. So let's see where this bond comes. So similar situation happens in the independent set model as well. This was in fact the first one where this kind of phase transition was observed due to a result of white. So here there's just one parameter lambda, and you can write down a critical value called lambda critical of D, where D is the degree of the graph. So so this was all for fixed degrees of fixed, so graphs of fixed degree at most. So the highest number of neighbors of a node is not allowed to be more than D. Then you get this line, and then you have hardness on one side, and algorithms on the other. Similarly, you look at the same things here, again, graphs of degree at most T for independent sets. Again, you can write down a number now, just a one-dimensional thing. Yeah, but this result tells you that you cannot run on the, so this line will keep shifting up and up as you increase D. So a beta lambda parameterization that is in the white region for a given D will not be for a larger D. And then you know that in general you cannot solve the problem unless you also are solving NP hard problem. So yeah, so there is just one critical activity, and again, so what White showed is that as long as you're on one side of the critical activity, as long as your lambda is small enough, smaller than this critical activity for that D, you have fast FP, you have an FP task, and again on the other side you have no efficient algorithms unless NP is equal to 1. So yes, so this correlation decay phenomenon underlies both these algorithms, and here is where it comes from. Here is where those lines and that critical activity comes from. So I just describe it for the independent set. Similar situation happens. Similar things happen for the anti-ferromagnetic Ising model as well. So what you do is you look at just the tree, not a general graph, but just the tree. Okay. So tree of arity D, and what you do is, so here's a tree of arity D. You look at it, you truncate it at, so it's infinite tree. You truncate it at level L, so at distance L from the root. And now you look at two different fixings of the root, the two extremal fixings of the root. So fix everything on the root to plus, or fix everything on these leaves at distance L to plus, or fix everything on those leaves to minus. So these two fixings will produce, by the Gibbs distribution, two different distributions in the upper part of the tree. And you just look at the marginal of this distribution on the root. So you have one marginal, which is this, when all the leaves at distance L are fixed to plus, and the other margin, which is when all the leaves are fixed to minus. And then what one can show is that so in the independent set case, when lambda is less than that critical activity, the same critical activity that appeared in White's result, then the difference between these two, so the two different conditional distributions, they become exponentially close. So it's exponentially in L. So L is the distance. So as the distance where you're making the fixing, as the boundary goes farther and farther away, the two distributions come close at an exponential rate when your activities are small. And as soon as you go on the other side of the threshold, these differences don't decay at all. They always remain bounded away from 0. And so this phase transition is what drives both the algorithm. So this side of the phase transition drives the algorithm. The other side drives the hardness result. Yeah, so that in some sense the tree is the worst. In some sense, the tree is the worst deregular graph for things like Markov chain Monte Carlo. So basically, the number of vertices at any given, the number of vertices in the boundary at a particular distance is the highest in a tree if you fix a degree, and that's what causes the tree to be the worst case. So you can sort of formalize this and show that although this analysis here was done only for the tree, when things are good on the tree, they're also good on general graphs of the same tree. Yeah, so I just wrote down an expression here, right? Okay, so the line in the anti-Ferromagnetic Ising model again comes from the same analysis. You look at the model in the tree, again figure out when these two regimes, and that's what the line represents. Okay, so this is for the anti-Ferromagnetic Ising model and for the hardcore or independent set model. In both these cases, if you recall, the situation is such that neighbors tend to disagree. So they're both anti-Ferromagnetic in some sense. Okay. So now we can ask what happens for the Ferromagnetic Ising model, and we will come to series of polynomials now. So it turns out that this phase transition that I showed you on the tree and so on, that happens also for the Ferromagnetic Ising model. It has the same kind of behavior. However, that transition does not. So in the two other models, we saw that the phase transition drives the complexity phase transition. On one side of the line, you have efficient algorithm. On the other side, you have provable hardness. The algorithm is provably hard. If you can solve it on the other side, then you can solve NPR problem. This does not happen for the Ferromagnetic Ising model. Here, it turns out that even though there is this correlation decay or uniqueness phase transition, there is the randomized MCMC based algorithm. So other two algorithms are not MCMC based. They're based more on things like belief propagation. But on this side, they're randomized Markov chain Monte Carlo algorithms, which basically cover the whole range. The whole range of parameters for the Ferromagnetic Ising model. So somehow there is this transition, but algorithms don't see it for the Ferromagnetic. However, it's only randomized algorithms that don't see it. So Markov chain Monte Carlo doesn't see it. But if you are looking at again those deterministic kind of algorithms, the kind of algorithms that worked for the independent set and the anti-Ferromagnetic Ising model, then they see that. And so the best known result, a deterministic algorithm for a long time for the Ising model, for the Ferromagnetic Ising model, just worked up to the uniqueness threshold. So the correlation decay threshold. So again, you can write down the correlation decay boundary. It looks something like this. So beta has to be close enough to 1. So the interactions have to be somehow weak. And there was a result which said that as long as you have that, you can do deterministic approximation without using Markov chain Monte Carlo, using this correlation decay based algorithm. But you cannot go beyond this transition. I mean, you don't know how to go beyond this transition. So somehow in the ferromagnetic case, we see that the presence of this transition, phase transition, which is a barrier to all algorithms in the other two problems, is a problem only to these algorithms. It's not a problem for Markov chain Monte Carlo algorithm. But yes, it's not an obstacle to actual approximability, but it is an obstacle to this particular kind of algorithm. So the question is there some other kind of deterministic algorithm which can match the MCMC based model? Are there other? So why is it that the deterministic algorithm seem to do better on the anti-ferromagnetic side, but not as well on the ferromagnetic side, which is supposed to be easier, and at least let's say on bounded degree graphs. So yes, so that's what we'll see. So we'll see that for the ferromagnetic Ising model, one can in fact go beyond the correlation decay threshold and get a deterministic algorithm using these zeros of polynomial idea. So the result is just that you can deterministically approximate the ferromagnetic Ising partition function on bounded degree graph, but with one condition, that the lambda is bounded away from 1. So lambda, remember, was so the weights look like, the weight of a sigma was number of plus spins in sigma and times number of this number of plus minus edges in sigma. So lambda equal to 1 basically corresponds to the case when plus and minus are completely symmetric in the distribution. And except for that case, as long as you are bounded away from that case, you can get a deterministic approximation. And as I said, correlation decay is sort of provably incapable, in fact, of matching this, but it's not as good as the MCMC based approximation. However, what the method that I'll show you can do is that it can also be generalized very easily, rather easily to hypergraphs. So we saw this Ising model which had pairwise interactions. I said that one can also look at higher order interactions, and this algorithm does generalize to these higher order interactions. On the other hand, the MCMC based approaches seem to have a barrier for that. So no Markov chain Monte Carlo based approach is known when the interaction size becomes bigger than 2. The order of the interaction becomes bigger than 2. So when you have at least 3 vertices interacting, it's not clear how to use MCMC, but this algorithm generalizes that. And it's going to be based on results on the location of complex roots of the partition function. And I'll just say as an aside that the idea of using complex roots for the partition function, in terms of algorithms, which was proposed by Barvinov, we'll mention later. But these things seem to have a nice connection with the complexity of approximated partition function, even on positive real values. In fact, and one can use them to show hardness results also. So there's some earlier work we had where we could use this information to prove hardness results. Here we'll use them to prove algorithms. And interestingly, so just to emphasize this, we'll use complex root, but we are only interested in real values of the parameter. I mean, positive real beta, positive real lambda. Those are the ones that make sense as probability distributions. But we'll somehow need to go through the complex plane. So let's see how this goes about. So this is so the first observation, which is just a simple observation, is that if what we are interested in is the relative epsilon 1 plus minus epsilon factor approximation to the partition function. That's just like asking for a plus minus epsilon relative approximation to the log of the partition function. For a small epsilon, those two things are the same. Okay. So how does one do that? So this idea, in fact, is quite old. It goes back at least to Yang and Lee. But the algorithmic, the realization that it can be exploited to find algorithms is due to Barvinov from about 3.5 years ago, and it's very simple in hindsight. So you take this, you want to approximate log of the partition function additively. So you just write down its Taylor series up to some fixed number of terms, and if you choose a number of terms carefully, then you can bring down the error as much as you want, provided the Taylor series is nicely converging. And yeah, so that's what it is. If the radius of convergence is capital R, and then the error that you have by evaluating the Taylor series at 0 is just this. It depends upon like exponentially in k. So k is the number of terms that you have, and some polynomial factor in n. But what is this capital R? So capital R is the radius of convergence of the Taylor series. This is basically the radius, the disk in which log z is analytic. The disk around 0, in which the radius of disk around 0, in which the log of the partition function is analytic. And this can be written in several ways. So log z is analytic in a particular disk if and only if the partition function can be shown to be non-zero in the same disk. So this is not hard to show. And this is just another way of writing this. So this name comes from something called stability theory, which we'll mention later, that this statement is also often written as the partition function is stable with respect to the disk of radius r. So the general point is that so here to show the